I'm going to look at several problems in which I separate variables in differential equations to work backwards and find the original general equation, and in some cases the particular solutions for those general equations. So my first differential equation here is dy dx equals 9x squared over 9y. Remember, this is just saying the derivative is 9 times the x value squared divided by 4 times the y value. So if I'm trying to find the slope of the original function at 1, 2, I can literally just substitute that in. So dy dx is equal to 9 times 1 squared over 4 times the y value of 2. And of course that's going to work out to be 9/8. So it can be relatively quick and relatively easy. For the second part of the problem, it asks me to find the particular solution or the particular equation for y if 0.25 is on the original graph of y. I don't have the equation for y. I'm going to need to work through this and figure out what's going on here. So the big thing here is I want to separate variables. So I have 9y, or I have dy dx. Wait, what? So I have dy dx equals 9x squared over 4y. And the first thing I need to do here is get the variables on the same side of the equation. But specifically, I need the y values on the side of the equation that has the dy. I need the x variables on the side of the equation that has the dx. So I'm going to multiply both sides by 4y. Okay, that's going to give me 4y dy equals 9x squared. I'm also going to multiply both sides by dx, which is going to give me 9x squared dx. Now I've got equal values. I take the integral of two equal things, I should get two equal values. So I can take the integral of both sides. The integral of 4y is going to be 2y squared. On the other side, this is going to be 9 over 3x cubed, so 3x cubed. I have a constant value. Essentially, I can combine those constants together on one side of the equation, and I'm going to do that as a plus c. And now I can go back in and substitute my point. The 0.25 is supposed to be on this graph, so I need to solve for c here. If I make x2 and I make y5, 5 squared is 25 times 2 is 50. That's equal to 2 cubed is 8 times 3 is 24 plus c. As a result, c is going to have to be 26. My particular equation in this case is 2y squared equals 3x squared plus 26. I may actually want to solve for y. If you need to solve for y, if it's not an ellipse equation or a hyperbola or something that's set up in a different format, you can certainly solve for your y variable as well. In this case, I'm going to divide everything by 2. And again, this can be formatted in several different ways. I now have y squared. Remember, technically the square root of a function is, when I take the square root, there are actually two. There's a positive and a negative square root. So technically, when I take both sides of the 1/2 power, there's going to be a positive and a negative. So I end up with y is equal to plus or minus 3x squared plus 26 all over 2 raised to the 1/2 power. So 2 equations come out of this. Again, this can be formatted in a lot of different ways. It really depends on what the question is asking you to do. But in this case, it sounded like I was being asked to solve for y, so that's what I did. Now, there are other types of equations, and you get all kinds of different types of solutions. Let me run through just a couple of those as quickly as I can here. And the process is more or less always the same. The challenge is going to be that there are special cases where you're going to have to use natural logs or something like that. Of course, the most standard case you're going to see is when you're told that the function y changes with respect to t in a way that's directly proportional to the original function y. So if I'm talking about the change in y with respect to time, that's going to be dy dt. If it changes in a direct proportion to the original function, so for example, if you have money in an account and it's increasing in a way that's directly proportional to how much money was in the account, that kind of thing. As I get more money in the account, I get a larger increase. As I have less money in the account, I have a smaller increase, that type of situation. Remember that that's always going to be the function, y multiplied by a constant. And this dy dt equals ky scenario is particularly special because if you notice, when I separate my variables, I'm going to end up with a 1 over y. So remember, you can't add and subtract to isolate that variable. You've got to divide. So I'm going to divide both sides by y here to separate my variables, okay? Dividing by y would be the same thing as getting 1 over y. That cancels. I'm going to multiply both sides by dt. And so what I've got here is a 1 over y dy equals k dt. Equal values. I can take the integrals of both sides. And this gets a little bit dicey because the integral of 1 over y, I can't write that as y to the negative 1 power because when I raise my power by 1, it's going to go to a 0 power. And so as a result, what I'm going to have to do here is write this integral as the natural log of the absolute value of y equals, this is going to be kt plus c on the other side. Make sure you can tell the difference between your t and your plus sign there. This is a log. It's a log base e. So I have the log base e of the absolute value of y equals kt plus c. Log form's not cutting it for you. Turn it into exponential form. This is e to the kt plus c power equals y. Keep in mind here, that's an absolute value of y. If I remove my absolute value, I've got to make my function positive or negative to compensate for the fact that I've taken out that absolute value. Okay? Where do I go from here? Well, one thing I know, if I've got values with the same bases, the exponents can be added. I could break this up as e taken to a kt power and e taken to a c power, the product of those two values. And I think I'm going to do that. I'm going to rewrite this as plus or minus, and I'm actually going to do my c first. I'm going to do e to the c power times e to the kt power equals y. Why am I doing this? Remember that e is a constant, all right? It's 2.718 extending out beyond there. C is a constant, okay? This whole value here is a constant. I can replace that with some other variable, okay? I can say, for example, that e to the c is equal to c1, and I can replace that, basically condense my constants down into one value. So what do I end up with? I end up with an equation telling me that y is equal to whatever my c value is. A lot of times we've used c naught to give that starting position. In this case, I created a c1 e to the kt. Okay? It's exactly the same formula that you've dealt with in population problems, in exponential growth problems back in Algebra 2 and Pre-Cal. You knew it as the PERT formula. You had a p and you had an r here as a rate. And that constant is a growth rate, and that actually is going to end up being your initial value, which you can find when you set t equal to 0 and work backwards. So anytime you see that a function's growth or rate of change over time is directly proportional to the function, you're going to end up working with this formula. Now in your book, they're going to write that as a c sub 0 because that's an initial value there. And that's why they ended up using that notation instead of using the c1 that I used in the 7. Again, if you're not asked to show that formula or to derive it, you can jump straight to using that formula, although in a lot of cases you're going to have a function that's maybe slightly different than what you began with, and as a result, you're going to need to know how to go through the entire process. Okay? Let me go through one more example here just to kind of run the gamut of types of things that could be asked. The final situation here I'm going to give you in this set of problems is dy dx equals 4xy squared. Same kind of thing as before. I've got to separate my variables. I'm going to divide both sides by y. In this case, divide by y squared. Multiply both sides by dx. Again, y squareds cancel. I'm going to write that 1 over y squared as y to the negative 2 dy equals 4x dx. Equal values means their integrals are going to be equal. So I can do something that looks like this. Remember, when you take the integral, you raise the power by 1 and divide by that new power. That's going to be a negative y to the negative 1 equals, raise the power here, divide by it, it's going to be 2x squared plus c. And again, you might want to write that as negative 1 over y equals 2x squared plus c. You're going to have to read the question to see what they're asking you to do. If they're asking you to solve for y, you've got all kinds of different possibilities here. Actually, you might want to multiply both sides by y. This whole thing being multiplied by y here. You would have negative 1 equals 2x squared plus c times y. You could divide by the 2x squared plus c. And you would actually find out that y is equal to negative 1 over 2x squared plus c. If you're given an initial point, you can put in that x and that y, you can solve for c, all kinds of different things. But the point here, the integrals work just like they normally do. You do have to watch your constant. You have to keep in mind when you've got a 1 over y or 1 over x or 1 over t or something like that, that you're going to have to use a natural log and the game changes completely. But most of these other cases, it's really just a typical integration, and a lot of times you can just use the power rule in reverse and it works out pretty nicely.